Hello.
Yes, ma'am.
Yeah, so I'm audible. Fine.
Yes, yes.
So we will
Yes, ma'am.
wait. We will wait till 7:05 and then we will start. Okay. Let's wait till
Okay.
that point. Anybody else joins? Okay. I can see many new people who joined this time. Many were not there in the last session, right? Okay. So hello everyone. I am Ritani Mandal. I am a PhD student in IISc Bangalore. I will be taking this course of yours in this one, like in these classes, which will be held on Monday from 7 p.m. to 8 p.m. We will be discussing about the questions which came in previous year, and we will be focusing on inorganic chemistry. Okay. Hello.
Yes, ma'am. Okay.
Yes, ma'am. Okay, ma'am.
Okay. So you guys must be so last day, like last week, I started with 2021 question paper. So, well, I'm sharing my screen. Can you see my screen?
No, ma'am.
No, ma'am.
Okay. Wait, I will cut the call and rejoin again. Okay. Is it visible now?
No, ma'am.
Okay. Shows that it's sharing. Hello, can you see now?
No, ma'am.
Yes, it is problem. I don't know, from my end it's showing that it's sharing. Hello. Uh, is it visible now?
Yes, ma'am.
Okay, very sorry. I don't know. There is some network issue in the hostel. Seems like that.
It's okay, ma'am.
Okay. So, actually, last week we started with solving 2021 question papers, like GATE 2021 question paper. So, we were focusing on inorganic chemistry questions. So, on last week, like we started from last week only, so we solved two questions. So, the first one was, which one of the following is a non-heme protein? And the other question which we solved was the rate of substitution reaction of COCN5 Cl whole 3 minus with OH minus to give COCN whole 5 OH 3 minus depends on what. So those people who joined the class, they from today onwards only, if you guys have any doubt in this question, you guys can ask me once after I finish, like after I teach, like do the other questions in this class. Okay. So today we will be doing like first question number 14. So actually I have a video like which I made on question number 14. So I will play that video. You guys can see that, and if you have any problem, any doubts in that, you can note it down and please ask me once that is played. Okay? Is it fine?
Okay, ma'am.
Yeah. So I am playing. Okay. Hello everyone. Today we will be discussing about this question which came in GATE 2021. The question is the delta O of CrH2O whole 6 3 plus. You guys can hear, right?
Yes, ma'am.
Plus CrF6 3 minus and CrCN whole 6 3 minus follows the order. So in this question we have been asked to write the order of this delta O for these three given complexes. So here we can see that all the three complexes which are given here are octahedral species. All of them are octahedral complexes. Okay. So we know that transition elements have 5 d orbitals, which are dxy, dyz, and dxz, dx square minus y square, and dz square. In a spherical crystal field, all the 5 orbitals are having same energy. But in octahedral crystal field, this degenerate set of orbitals will split into two sets, T2g and EG. T2g will have dxy, dxz, and dyz, whereas EG consists of dx square minus y square and dz square. T2g is having pi type character, whereas this EG is sigma type. The difference between this T2G and EG set is the delta O value. This is also called this crystal field splitting. So this delta O depends on various factors. They are charge on the metal, principal quantum number, and ligand field strength. So let's start with comparing this metal charge. So for the first complex given CrH2O whole 6 3 plus, if we consider that chromium is having an oxidation state of X, then X plus, since H2O is a neutral ligand, it will carry a charge of 0 and the overall charge of this complex is plus 3. So X plus 0 is equal to plus 3, or X is equal to plus 3. So in this complex, chromium is present in plus 3 oxidation state. Now for this complex CrF6 whole 3 minus, if we consider this having X oxidation state, then X plus 6 into fluorine carries minus 1 charge each. So this equal to overall charge is minus 3. So X minus 6 is equal to minus 3, or X is equal to plus 3. So here also chromium is present in plus 3 oxidation state. Now for this complex CrCN whole 6 whole 3 minus, X plus Cn also carries a charge of minus 1 and overall charge is minus 3. So X minus 6 is minus 3, or X is equal to plus 3. So again in this case as well, chromium is present in plus 3 oxidation state. So here we can see in all the three complexes, the charge on the metal is same, that is plus 3. So on the basis of this factor, we can't compare the given three complexes. The next factor is principal quantum number. So in all the three cases, we can see that chromium is the transition metal present. It is a 3D transition element. So we can't compare on the basis of this as well. Now next, moving on to the ligand field strength. So here we can see that all the three complexes have different ligands present in them. So this has H2O as the ligand, this has fluorine, and this has Cn. H2O is a sigma only type ligand. Fluorine is a pi donor ligand. And Cn is a pi acceptor ligand. So for checking this ligand field strength, if we look on this spectrochemical series, we can see, we know that on going from left to right along this series, that is on going from pi donor ligands to pi acceptor ligands, the ligand field becomes strong. So pi acceptor ligands are strong field ligands, whereas pi donor ligands such as halides are weak field ligands. And H2O somewhere it falls in between. Okay, and it has only sigma only type of interaction with the metal. Cn minus is a strong field ligand and fluoride, this is a weak field ligand. So if there is only sigma type of interaction between the metal and the ligand, then in an octahedral field we know that the degenerate d orbitals split into T2G and Eg, and the energy gap between them is the delta O. But if we have pi donor ligands like the halides, because of the presence of lone pairs in them, and as they are electronegative, so they lie lower in energy, and because of this field, px and py orbital, px and py are filled if we consider pz, like if we consider the z as the internuclear axis. Then px and py are filled and they have the correct symmetry to interact with the metal T2G set of orbitals, and they a combination of bonding and antibonding orbitals will result from them. So this is the bonding T2G and this is antibonding T2G star. Since the antibonding T2G star has closer energy with that of the metal T2G orbitals, therefore it will be largely metal based, and this is the HOMO. This energy of Eg orbitals will remain unchanged, and as a result of this we can see that in case of pi donor ligands the delta O value is decreasing from sigma only type of interaction to pi donor ligands, whereas in case of pi acceptor ligands we know that here in the pi acceptor ligands they have a vacant pi star orbital. Since this is vacant, so they lie higher in energy, and here also this have suitable symmetry to interact with the metal T2G orbital, and as a result of which a bonding set of T2G and antibonding T2G star orbitals will result. And since in this case the bonding T2G lies closer in energy to the metal T2G orbitals, therefore this T2G set will be highly metal based, and now this is the HOMO. So on moving from just sigma type interaction ligands to pi acceptor type ligands, we can see that here the delta O value increases. Okay. So in this question, we saw that chromium had +3 oxidation state, so it was a D3 system, and therefore we can see that delta O decreases in case of fluoride. For H2O, it will lie somewhere in between, and for pi acceptor Cn minus, it will be the maximum. Now going back to the question, therefore CrCn whole 6 3 minus will have the maximum delta O. This CrH2O whole 6 will lie somewhere in the between, and CrF6 3 minus will have the least value of delta O. So option number C is the correct answer. For knowing more about this, please refer to lecture number 35 on coordination chemistry. delivered by Professor Debashish Ray from Department of Chemistry, IIT Kharagpur. The link for the video is given here. Please go ahead and watch the video. Thank you. Hello.
Yes, ma'am.
So was it clear?
Yes, ma'am.
Anybody having any questions from this? Hello.
No, ma'am.
Okay, so
Hello, ma'am.
yeah. Hello.
Ma'am,
Yeah, tell.
yeah, ma'am. In a pi donor type of ligand, uh, how did you place those electrons filling, ma'am? I didn't understand filling of electron.
Wait.
Yes.
So in this case, you are asking, right?
Yes, ma'am.
So see, pi donor means like halides will be pi donor type of ligands. Okay, they have filled pi orbitals plus they have lone pairs. Okay, so because of the presence of those lone pairs, it will be it will be lower in energy. Here you can see that this pi filled pi orbitals are low lying. Okay, so what happens is that this pi orbital is suitable to yeah. So one thing is that when this in octahedral field, it is splitted into T2G and EG. This T2G orbitals have pi type of character, whereas EG have sigma type character. Okay, so that's why here this T2G will interact with this filled pi orbitals to give a set of bonding as well as anti-bonding orbital. Okay, so from here you are like so now since here it was filled, so 6 electrons came from here. So this is an example for D1 type of complex. Okay, so this 6 electrons from this ligand orbital, and then since G1 system, 1 electron will go to this antibonding T2G star orbital. Okay, so since now
Only,
since yeah.
only three ligands will participate in pi donor.
No, no, no. It's not like that. CR, like, let's say it is CRF6, na? So all are participating in that. Actually, okay, you are saying that if they are giving 2 electrons each. That is what you are saying?
Yes, yes, ma'am.
Okay. So actually, in ML6 type of ligands, we consider that like they are giving, we are considering one only maybe. Okay, so I will get back to you on this, but from 6 ligands, like you can refer to RP. This figure is taken from Atkins. Okay, so you can refer to Atkins as well as RP Sarkar. So there, how they explain is that 6 from 6 ligands. So these are coming here, and then from T2G, this one will go there. So now, after that, what happens is that this T2G is the gap between this metal T2G and this molecular orbital T2G, it is more than the gap between T2G and T2G star. So therefore, this T2G star will be highly metal based. Okay. So therefore, now we will consider this as the new HOMO. This is our HOMO, and this EG will remain unchanged. So from here to like now the new delta O octahedral splitting is this. So we can see that for pi donor type of ligands, it decreased from this much to this much. And for that thing, I will, what is your name? I will definitely get back to you. Uh,
RP, ma'am.
okay. I will let you know. The other things are clear?
Yes, ma'am. Yes.
Anybody else? Okay, then can I move on to the next question?
Yes, ma'am.
Okay. So next question which we will be discussing is uh, this question number 25. Okay. Wait a second. So in question number 25, they are asking for the spin only magnetic moment of COH2O whole 6 2 plus rounded off to one decimal place is how much? We have to give the answer in Bohr magneton. Okay. So first of all, like when an electron orbits around, like it spins around an orbit, what happens is that it will have a spin angular momentum as well as an orbital angular momentum. So the spin angular momentum arises from the spinning motion of the electrons across its own orbit. Here we can see that when an electron is orbiting, it spins around its own axis also. So this motion gives rise to the spin angular momentum, and the orbital motion across this, if we consider this as the nucleus, this motion across this orbit gives rise to the orbital angular momentum, and they gave their corresponding or magnetic moments. Okay, so we have spin magnetic moment as well as orbital magnetic moment. Generally in case of 3D, hello.
You are audible.
Okay, so generally in case of 3D transition metals, the orbital contribution is less as compared to uh, 4D or 5D. Okay,
Voice is not audible, ma'am.
what? I'm not
Yes.
audible.
Okay.
Am I audible?
Ma'am, your voice was not audible for last minute.
Okay, so till what point you guys heard?
Ma'am, please start the solution part again.
Okay. Then okay, so this is for the just the basics. Why this magnetic moment arises? It is due to the spinning motion of the electron across its own axis, and the orbital angular momentum generates from the motion of the electron across that orbit. Okay, so and generally in 3D transition metals, we see that the orbital contribution is less as compared to 4D and 5D transition metals. So now this is the formula of our spin only magnetic moment. So mu spin only is given by 4 root over 4s into s plus 1, where s is the spin quantum number. This mu b is Bohr magneton. This is a constant value which is 9.274 into 10 to the power of minus 24 joule per Tesla. Okay, so this spin value, actually every electron has a spin of 1 by 2. So therefore S is equal to, like, total spin value is equal to n by 2, where n corresponds to the total number of unpaired electrons. So now if we substitute the value of S is equal to n by 2 in this equation, we will get mu spin only value as root over n into n plus 2 Bohr magneton. So here in this question, the given complex is COH2O6 whole 2 plus. Okay. So cobalt is how many electron system? Anybody? Hello? Hello? Am I audible? Yeah. So yeah, I was asking that cobalt is generally, like, a free cobalt is how many d electron species? Anybody can answer.
What, ma'am?
I am asking that in a free cobalt complex, what is like cobalt is how many d electron system? How many electrons are there in the d orbital?
Ma'am, valence electrons.
Ma'am, D7.
So in a normal free ion, like if cobalt is free, it has 3d7 4s2 configuration. So here in this case, we can see that cobalt is present in an oxidation state
Ma'am,
of
you've
plus
stopped
2.
sharing.
What?
You have stopped sharing, ma'am.
No, I have not stopped. Okay, I will reshare again. Wait. Visible? No?
No, ma'am, you are not visible.
Okay, just hold on. Well, I am going out and coming again. Okay. I seriously don't know why this is happening. Now I think now it is visible. Is it? Hi,
Hi,
now
now
it
it
is
is
visible,
visible,
right?
right?
Yes, ma'am.
Okay. Okay, so where we were? Hmm. So here, in the given compound, cobalt is in +2 oxidation state. Okay. So generally, cobalt is a D7H2 system. Since 2 plus oxidation state, so 2 electrons are going, and now it is a D7 complex, right? So also here we know that in COH2O whole 6 2 plus is an octahedral complex. In octahedral crystal field, it will be splitted into T2G and EG, as we discussed in the last question also, right? So here what will happen is, uh, first all the like in T2G all the d orbitals will get filled. So 1 2 3 4 5, and now since water is a weak field ligand, so what will happen is that instead of pairing up, it will give uh, like, see, first we filled D7 7 electrons in T2G and EG orbitals. Now since water is a weak field ligand, instead of these two pairing up, they will stay like this. By this I mean that this is a high spin complex. Okay. So since this is a high spin complex and the electrons are distributed like this, then can someone tell me what is the total number of unpaired electrons?
3.
Okay. Number of unpaired electrons are 3. So we know now that the putting that in the equation which we discussed before, mu spin only is given by root over n into n plus 2 Bohr magneton, right? So the number of unpaired electrons is 3. So here we will just put the value 3 into 3 plus 2 Bohr magneton, which is equal to root over 15 mu b. Can anyone tell me what is the answer? Just calculate. Huh? Excuse me.
3.87.
Okay. So now in the question we have been asked to round off to 1 decimal place, right? So if we round off 3.87 to 1 decimal place, it will be 3.9. It will be 3.9 Bohr magneton. For getting more insight onto this, you guys can refer to Coordination Chemistry lecture series, which is given by Professor Debashish Ray from Department of Chemistry, IIT Kharagpur. In lecture number 29, he has discussed about this magnetic moment and all those things. He has discussed about magnetic chemistry. So now, do you guys have any doubt in this question? Hello?
No, ma'am.
No, ma'am.
Everyone clear then?
Yes, ma'am.
Okay, so I am moving on to the next question. So the next question which we will be solving today is question number 27 from 2021 GATE exam. Okay. So here the question is, the yellow color of an aqueous solution of K2CrO4 changes to a red-orange solution upon the addition of a few drops of HCl. The red-orange complex, the oxidation state of its central element or elements, and the origin of its color respectively are. So here we have to answer first that what is the red-orange complex which is forming. Then we have to say what is the oxidation state of the central element of that compound, and also we have to tell about the origin of its color. Okay, so first let's just see the reaction which takes place on adding HCl to an aqueous solution of K2CrO4, which is potassium chromate. Okay, so when we add concentrated HCl to K2CrO4, we get potassium dichromate, which is K2Cr2O7. This potassium dichromate is red-orange in color. This is the reason why on adding concentrated HCl to K2CrO4, which was yellow in color, it changes to red-orange. It's because of the formation of K2Cr2O7. So this gives us the answer of the first part of the question, that is dichromate ion, right? The other options given are chromium chloride, perchlorate ion, and chromic acid. We saw that the reaction of K2CrO4 with HCl gives K2Cr2O7. This is a dichromate ion. So this gives the answer of the first part. Now moving on to the oxidation state of a central element. Okay, so here the central element is chromium, right? So K2Cr2O7, this can also be written as Cr2O7 2 minus, right? So now everyone can consider this chromium is in X oxidation state, and can you guys just try out like what is the oxidation state of chromium in this complex, because the first question which we solved was similar, right?
Plus 6.
What?
Plus 6.
Yeah. So to everyone here, like each, if we consider each chromium is present in plus X oxidation state, then 2X plus oxygen gives a charge of minus 2. So 7 into minus 2, and the total charge of the complex is minus 2. So this will give 2x minus 14 is equal to minus 2, or 2x is equal to 12, or x is equal to plus 6. Right. So here this means that all the chromium, like both the chromium present in this complex are in plus 6 oxidation state. So this gives us the answer of the second part as well. Oxidation state of the complex is plus 6. Fine. Next, moving on to the origin of its color. So for that, for origin of its color, we can see that two type of options are given. One is DD transition and the other is charge transfer, right? So I think we all know what is DD transition. Basically, DD transition means like in a certain crystal field, what will happen is that the d orbitals will be splitted into, like the degenerated d orbitals will be splitted into different set of orbitals, and the transitions which take place between them gives rise to the DD transitions. Like in case of octahedral symmetry, what happens is we have T2G set of orbitals, we have EG set of orbitals. Let's say we have an electron, one electron in T2G, then the transition from this T2G to EG will give, like these type of transitions are known as DD transitions. Okay. Now the next type of transition are charge transfer. In the option, the other thing given is charge transfer. So what is charge transfer? Mainly we can classify like mostly we will see ligand to metal type of charge transfer, and metal to ligand type of charge transfer. Okay, so what is ligand to metal charge transfer? That is LMCT. Is that when when the ligand molecular orbitals are full and the metal is present in a very high oxidation state, that is they have either empty or partially filled metal d orbitals, then the molecular orbital of the ligand will transfer charge to the metal empty orbital, and this will give rise to color. Okay, so this type of transitions are called ligand to metal charge transfer. The examples of such ligands are halides, O2 minus, H2 minus, like this. And the other type, which is MLCT, that is metal to ligand charge transfer. In this case, what happens is that the like the ligand possess a low-lying empty orbital, like if we consider the case of pi acceptor ligands. Okay, so in pi acceptor ligands, we have this empty pi star orbitals, so they can accept electrons. And if the metal is lying in low oxidation state, then what can happen is that the metal can transfer its electron to the empty orbital which is present in the ligand. Okay, so the example of such ligands are pi acceptor ligands mostly, which are Cn minus, CO, NO, etc. Okay, so now the question is DD transfer or charge transfer. So as you guys just now only you told that in this case chromium is present in +6 oxidation state, right? And the electronic configuration of chromium is 3d5 4s1. So if it is present in +6 oxidation state, that means all the 6 electrons are going. Okay, that means now there is no electron in the d orbital, right? So if there is no electron in d orbital, no, like then how can dd transition take place, right? So in this case, the color which we are observing for red, like this red orange color, this is arising from transfer of charge from ligand to metal. Okay, so I gave example here that like see oxygen type of ligands can do that. So here O2 minus is the ligand, and since the metal is present in +6 oxidation state, it has empty d orbital. So in this case, ligand to metal charge transfer is taking place, because of which we are getting this intense color. Okay, so moving on to the question. Now we know that the complex which is formed on adding HCl to K2Cr O4 is dichromate ion K2Cr2O7. The oxidation state of both the chromiums are +6 in this complex, and the color which we are observing is due to charge transfer from ligand to metal. So this is it. So any question for this, like any doubt for this question? Hello? Hey, am I audible?
Yes,
It's
ma'am.
okay.
It is understandable, right?
Yes, ma'am.
Yes, ma'am.
Uh, Clear to everyone? Shall I move on to the next question?
Ma'am,
Uh, yeah.
ma'am, can you please tell me something about Laporte transition in DD transfer?
Laporte transition and DD. Okay, so the next question which we are going to solve has that in it. So I am going to explain in that. Okay. Still, if you have any doubt, you ask
Okay.
me. Okay. We will take up the next
Yes,
question which
ma'am.
implies that rule. Okay. So the next question which we will be discussing is question number 42 from GATE 2021 paper only. Okay. So here in this question, they are asking the correct order of increasing intensity of the UV visible absorption bands for the ions titanium H2O whole 6 3 plus, MnH2O whole 6 2 plus, CrO4 whole 2 minus and NiCl4 2 minus follows which order. Okay, so we have to write the increasing intensity for the UV visible absorption bands for these complexes. Okay, so we know as per like all of us are familiar with Lambert-Beer's law. So this states A is equal to epsilon Cl, where A is the absorbance, epsilon is the molar absorptivity. So this basically gives this intensity, and then C is the concentration in mole per liter, and L is the path length of the sample. So here we have been asked to write the order of this epsilon. So now this selection rules, okay, which you were asking. So first, there are two type of selection rules. One is this spin selection rule, and the other one is this Laporte selection rule. So spin selection rule states that transitions which have the change in spin number equal to 0 are only the spin allowed transitions. Okay, so transition is allowed between two energy states which have same spin multiplicity, that is transitions resulting in a change in the total number of unpaired electrons are spin forbidden. And the next one is Laporte selection rule. So this states that the transitions for which delta L is equal to plus or minus 1 are allowed. So in a centrosymmetric environment, an allowed transition must involve orbitals having different symmetry properties with respect to the inversion center. That is, transitions are possible from Girardet to Ungirardet or Ungirardet to Girardet. These type of transitions are Laporte allowed, and if we have G to G or U to U, like Girardet to Girardet or Ungirardet to Ungirardet, then these type of transitions are Laporte forbidden. So since d orbitals okay, since d orbitals are G type, therefore a DD transition is forbidden. Not only DD transition, like F to F transition is forbidden, S to S transition is forbidden. Okay, so anything having like same symmetry, if the transition is taking place between two same symmetry, it is forbidden as per the Laporte selection rule. But for a complex which don't have any center of inversion, okay, so if a complex has no center of inversion, then this Laporte selection rule does not apply. Now moving on to the complexes which are given in this question. The first one, let's take CrO4 2 minus. Okay, so in CrO4 2 minus, can you guys tell me the oxidation state of chromium?
+6.
Okay, so just now we discussed that when chromium is in +6 oxidation state, there are no d electrons, and oxygen is able to do ligand to metal charge transfer, right? So in this case, what happens is that therefore here the color which we observe is due to LMCT LMCT transition. Okay, so for this ligand to metal type charge transfer, uh, these type of transitions are both spin allowed as well as Laporte allowed. Okay, now moving on to the next complex, which is NiCl4 2 minus. Can anyone tell me the geometry of this complex?
Square planar.
Okay, no, it's not square planar, it's
Tetrahedral.
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 So it is tetrahedral. In tetrahedral crystal field, we have E and T2. Okay. The difference between octahedral and tetrahedral is that tetrahedral complexes do not have any center of inversion. Okay. So, since tetrahedral complexes have no center of inversion, so in this case, see here also what will happen is, like here nickel is having how many electrons? Anyone?
3D8, ma'am.
Okay.
DX system.
Okay. So since it is a D8 system, that means D to D transition will take place, right? And DD transitions are Laporte forbidden, right? We discussed that. So DD transition, okay, let me draw 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here what will happen, that one of these electrons can go to this T2 set, and that electron will also have the same spin, right? So we can see that there is no change in spin multiplicity, but the transition is a D to D transition. So this means since delta S will be 0, therefore it is a spin allowed transition, but it is a Laporte forbidden transition.
But there is no center of inversion, no, ma'am.
Yeah, that's what we are talking about. So if we consider this as an octahedral complex, then we will say that this is Laporte forbidden. But since it is a tetrahedral complex, that's why only, like, we have this difference between octahedral and tetrahedral. If it would have been an octahedral complex, then it will show less intense color than the tetrahedral complex. Okay, so since there is no center of symmetry, this rule will not be applied, and tetrahedral, like we will see an more intense color for tetrahedral complex in comparison to that of an octahedral complex. Now moving on to the next two complexes, TiH2O whole 6 3 plus and MnH2O whole 6 2 plus. So both of these complexes are octahedral, right? So titanium 3 plus is how many electron system?
D1, ma'am.
D1 system.
Okay, so this is T2G and EG. So here what transition can take place? This electron from T2G can move to EG. So here delta S is 0, but delta L is not plus minus 1, right? So this is Laporte forbidden and spin allowed. Now moving on to the next complex, which is MnH2O whole 6. Tell me, for Mn2 plus how many electrons are there?
5.
Okay,
D5.
D5. So what will be this? Like 1, 2, 3, 4 and 5. So 3 electrons in T2G set and 2 electrons in EG set. So in this case, for a transition to take place, what will happen is one of the electron has to flip its spin, right? It have to go like this. That means delta S is not 0 in this case. Neither is delta L equal to plus minus 1. So in this case, it is both spin and Laporte forbidden. So now I think you guys can tell me the order of the intensity. See, for titanium, what we saw, it was a D1 electron system. It is an octahedral system. Here, it was spin allowed, but Laporte forbidden. For manganese complex, it was both spin forbidden as well as Laporte forbidden. For chromium, it is a charge transfer complex. It is both spin allowed and Laporte allowed. And for nickel, Cl4 2 minus, it is a tetrahedral complex. Therefore, spin allowed and Laporte rule does not apply for this case. Therefore, the correct order will be the most intense will be CrO4 2 minus, which is because of charge transfer. Then it will be the tetrahedral complex NiCl4 2 minus. Then the DD transition in this octahedral complex TiH2O whole 6, since in this case it is spin allowed but Laporte forbidden, and the least will be for manganese, because in this case it is both spin as well as orbital as well as Laporte forbidden. Is it clear?
Yes, ma'am.
Now someone was asking me about this selection rule. Do you have the question? Do you still have any question?
No, ma'am, no.
So is it clear to everyone?
Yes, ma'am.
So it's already 8:30. Wrap up today's session. Thank you for joining everyone, and yeah, happy Independence Day to all.
Same to you, ma'am.
Happy Independence Day.
Okay,
Thank
bye
you,
bye.
ma'am.
So yeah, one thing, if you guys have any queries or anything, you guys can contact me. I can share my mail ID with you. Okay, somebody wrote something in chat box also, which I did not read. Okay. Mani Bharati, you wrote some 3.9. What is this?
Ma'am, it is
Oh,
magnetic.
answer, magnetic mod. Okay, okay, thank you. I saw it just now. Okay, so if you guys have any doubt or you guys can give any better suggestion with what I can come up to, you guys can let me know. Okay, and yeah, mainly now I am solving this 2021 inorganic portion. So it will be better if you go through that question paper and come to the class. You guys will be familiar whatever I am talking about. Okay,
Okay, ma'am.
okay, bye bye.
Thank you, ma'am. Bye.
Ma'am.